pleasure to have our second speaker for today, who's Evgeni Dimitrov, and he'll be speaking to us about two-point convergence of the stochastic six-vertex model to the Airy process.
So thank you very much for the introduction and for the invitation to speak. It's a great pleasure to be giving this talk. So as Ivan said, I will be discussing today recent work in which we show a two-point convergence of the stochastic six-vertex model to the Airy process. So the outline of the talk will be as follows. I'll first tell you what is the stochastic six-vertex model in the quadrant and what we can prove about it. Afterwards, I'll tell you a little bit about the connection between this model and the ascending Hall-Littlewood process, which is actually in the paper the main thing that we work with. Afterwards, I'll give you what the sort of formulas we can obtain for the ascending Hall-Littlewood process using the McDonald difference operator. So I will not be deriving these formulas today. So I'll just tell you what they are and we'll try to understand what they mean. And the thing that I will try to spend a little bit more time on is the asymptotic analysis of these formulas, which I think is the more interesting part. So what is the stochastic six-vertex model? So it was introduced by Gwa-Spohn in '92, and it's a very simple statistical mechanics model. So you have a path ensemble. So these are just paths that move to the right and up. So all the paths, they enter the left boundary of the first quadrant, and they just move to the right or decide to turn up, and there's no paths entering from the bottom. So this is the state space of the model, and sort of the combinatorics of it demand that no two paths. So paths are allowed to share a vertex, but they cannot share an edge. So this rule basically tells you that you have an arrow conservation at each vertex. So the number of incoming arrows needs to be equal to the number of outgoing arrows. And so the possibilities of what can happen at each vertex, there's 6 of them, and I've listed them here. So you can either have no arrows coming in and no coming out, 2 coming in, 2 coming out, and 4 other possibilities of a single arrow coming in and leaving the vertex. So this is why the model is called the six-vertex model. Okay, so this is the state space, and the probability measure that we put on this space depends on 2 parameters, little b1 and little b2. And the way you build this model is basically in a Markovian way. So you just do it one diagonal slice at a time. So let's say you've built the model up to this time. And what you see is that in this triangular region, you've specified the vertex configurations at each of these lattice points. But on this diagonal, you've only specified the incoming arrows at each vertex. And then what you need to do is you need to just go one vertex at a time and complete the arrow configuration using this cheat sheet. So this is your formula sheet. And so you look at each vertex and you see, okay, there's 2 arrows coming in. So I need to complete it with probability 1 to this vertex. Or here you have an empty vertex, you complete it with probability 1 in this way. So there is a single choice if there's no arrows coming in or there's 2 arrows coming in. And if there's a single arrow, so let's say here you have a single arrow coming horizontally, so there's 2 ways to complete it. So with probability B2, this arrow propagates to the right, and with probability 1 minus B2, it flips up. And similarly for vertical arrows. Now all of these choices, they're made independently. So you just toss some Bernoulli coins and you update this slice and you move and propagate the process forward. And these are consistent and define a measure on upright paths in the entire quadrant. Okay, so this is one way to interpret this model. I'll next explain a different one in which you can think of this model as an interacting particle system, and I'll try to explain how it's related to probably the most familiar example people know, which is the ASEP. So let me remind you you heard it in Elisa's talk, but I'll show you the picture once again. So the ASEP, or asymmetric simple exclusion process, is a simple interacting particle system in which the particles occupy some integer sites, and each particle carries with it 2 clocks. And these clocks, so there is a left clock and there is a right clock, and they are ringing at exponential times with rate L and R. And when the left clock rings, the particle tries to jump to the left by 1. And when the right one rings, it tries to jump to the right by 1. And the jump is successful as long as the site to which the particle wants to jump is free. So here, for example, the right jump is suppressed because there is another particle that's sitting at this location, and so the particle jump is suppressed. Okay, that's the exclusion rule. And the initial condition that corresponds to the six-vertex model that I described in the previous slide is the step initial condition, where initially all the particles occupy the non-positive integer sites. And in general, up to rescaling of time, one can always assume that the right jump rate is 1 and the left one is a number little t between 0 and 1, so that the particles tend to unpack. So they tend to jump to the right a little bit more than they tend to jump to the left, so that they can unpack from this step initial condition. So this slide is supposed to basically convey two things. The first one is how to interpret the six-vertex model as an interacting particle system. And the way you do this is by interpreting the horizontal direction as space and the vertical direction as time. So the locations of the vertical arrows are basically the locations of your particles. And then you kind of do a discrete time update where the particles somehow move in the upward directions. Hopefully it's clear from the picture that you can at least heuristically make sense of this as a particle ensemble. But in fact, it's you can really think of this model as a discretization of the ASEP. Namely, there is a limit transition that takes you from the six-vertex model to the ASEP. And the limit transition involves taking the parameters B1 and B2 to scale down to 0, let's say at some rate epsilon. Now, this connection to the ASEP was probably already known by Gwa-Spohn, but it was articulated in this paper by Borodin-Corwin-Gorin and proved by Agarwal for general initial conditions, fairly general initial conditions. Let me just kind of pictorially explain to you how the argument goes. So if you scale B1 and B2 to 0, so you're basically prohibiting these vertical double steps and these double horizontal steps in the model. Now, if you look at kind of time order 1, then basically all of your particles are going to do, they're just going to have these zigzag trajectories. So you kind of, your reference frame is moving diagonally, okay? And this is what's happening if time is kind of order 1. But if time is scaled like epsilon inverse together with this scaling, then every once in a while you will see one of these double vertical jumps. So for example, here you can have a double vertical jump, it's the red arrow, and then you continue propagating diagonally. And every once in a while, you'll see a double horizontal jump. Like here, you have this blue one doing. And what you should notice is that, you know, in a moving frame, jumping twice to the right is like a jump by 1. And staying put, which is what this red arrow is representing, is like a jump to the left. So hopefully, kind of just by the picture, you can visualize that this is really going to go to the ASEP dynamics. Okay. Now, another way to interpret the model is in terms of its height function. And the height function is basically at you fix some level, let's say M, and you just count at a given location the number of vertical arrows to the right of this location. So for example, here there are 6 arrows to the right of this location. I didn't draw all of them, but hopefully you can visualize that there's some additional ones over here. And then every time you kind of overcome an arrow, the height function drops down by 1 because there's 1 less arrows that you're counting. So here it goes from 5 to 4. Now in this way, you obtain a random continuous curve that's piecewise linear. You know, compared to the one that Elisa drew for you, she had slopes plus and minus 1. I prefer slopes minus 1 and 0. So that's a choice that doesn't matter. Of course, it's up to an affine shift, the same thing. But the point is that understanding the particle configurations or understanding the height function are equivalent. One, you know, they encode the same information. It's just a little bit more convenient to formulate statements in terms of the height function. So what is the main result that we prove? So first you fix the parameters B1 and B2 to be some numbers between 0 and 1. So the condition that B2 is bigger than B1 is corresponds to this particles tending to move more to the right, because you're starting basically from step initial conditions and you want them to unpack. So that's this condition here. You also introduce 2 auxiliary parameters. One of them is called A and the other one is called little t. Now the little t is nothing but the asymmetry parameter in ASEP, for example. So kind of t being 0 will take ASEP to TASEP, or will take the 6-vertex model to the 5-vertex model. So this is, t being 0 is what's called the free fermion point. And your assumption is that both of these parameters, A and T, are sufficiently small. Now, I want to emphasize that the first condition is somehow technical and can be overcome even right now. And it's mostly assumed so that, you know, arguments in the paper can be simplified. The second one is a little bit more delicate. So it seems to be somehow entrenched in many of the arguments, and one really needs to think about how to push this parameter away from zero. But but the point here is that your assumptions are that somehow your model is sufficiently close to the free fermion point, but still bounded away. So using this, let me introduce some notation. So you fix two times, S1 and S2. So these are just real numbers. S1 is bigger than S2. And you introduce these points, little n1 and little n2. And what they are is just m, which is playing the role of time in our model, shifted away by S1 times m to the 2/3. So you're doing this m to the 2/3 shift away from the main diagonal. And then you form these two variables that are basically the height function, but appropriately shifted in scale. So you just evaluate the height function. Again, the second argument here should be interpreted as time. That's the vertical direction of the model. And you're looking at the spatial point n1, and then you subtract some leading order asymptotics. So these coefficients f1, f1 prime, and f1 double prime, they're listed here. And it's not important what they are. The only thing I would point out is that they only depend on the parameter little a. They don't depend on the t. Okay. And so if you subtract this leading order asymptotic, which is deterministic, the residual fluctuations are of order m to the 1/3. So you scale down by m to the 1/3. So now you have order 1 fluctuations, and maybe multiplied by an additional convenient parameter sigma that's written here. And you do this for the point n2 as well, calling the resulting variables x tilde and y tilde. And then what's the statement? The statement is that as m tends to infinity, these two variables, x tilde and y tilde, jointly converge to the 2-point distribution of the Airy process at time tau 1 and tau 2, where tau 1 and tau 2 are related to the s's through these simple equations. Okay, so that's the statement of the theorem. So are there any questions about the statement of the theorem? I'll have a bit of discussion about what it means, but let me ask if there's questions. Okay, so in this theorem, the only thing I didn't tell you is what's the Airy process. I will not delve into the details, but it's one of the known universal scaling limits in the KPZ universality class. It was first introduced in the paper by Perhofer and Spohn in the context of the polynuclear growth model. And also some of its basic properties can be found in this paper by Johansson. For example, that it's a determinantal process whose correlation kernel is a trace class operator, and there's some contour integral formulas there. So the object has also been studied significantly here. And here I've just written down the joint cumulative distribution function, which is some Fredholm determinant expansion formula involving the extended Airy kernel, which itself has a contour integral representation involving the Airy functions. Let me make a few remarks about the main result. So the 1, 2, 3 scaling has been predicted by KP's universality. So what is this 1, 2, 3 scaling? So here again, m is time, so it's scaled like m. And then the spatial direction, which is this n1, is scaled like m to the 2/3. And the fluctuations are scaled like m to the 1/3. So that's the 1, 2, 3 scaling that has been predicted by KP's universality. Previous results related to the 6-vertex model
Evgeni, you muted yourself. Or I'm not getting any sound from you right now.
You can try unmuting him by clicking.
Well, I can ask him to unmute, but I can't force him to unmute. Okay. We're still not getting any sound.
How about now?
Oh, yes, now. I was going to say the result speaks for itself, but it's even better if you can speak for it.
Sure. Okay, so again, hopefully this will not happen again. Fingers crossed. But right, so previous results on the six-vertex model include the one-point convergence to the one-point Airy process or the Tracy-Whittam distribution in the paper by Borodin-Corwin-Gorin. And what I want to emphasize is that this is sort of the first rigorous multi-point result for a positive temperature model in the KPZ universality class. So there are previous works that prove multi-point convergence, but they are all limited to determinantal point processes. So lozenge tilings, polynuclear growth model, ASEP, these types of models, all of them are determinantal, and this is the first non-determinantal result. But the other thing I want to mention is that there are previous works related to positive temperature models that are in the physics literature. So here, this list is not comprehensive. It includes mostly the two-point results involving the KPZ equation in the physics literature, the Dotsenko, Prolak and Spohn, and Imamura, Sasamoto, and Spohn. And there's also from the math side, the work on the log-gamma polymer model by Nguyen and Ziguras. So the physics works, as I said, focus on the KPZ equation. They're based on more replica approach, Beth and Zat's techniques. The math work is significantly more rigorous, but the asymptotic analysis falls a little short near the end, so they cannot complete the proof, but they do important steps towards obtaining the convergence to the Airy process. So to give a general outline of the proof, so there are a few steps, and most of them are actually fairly reasonable and not wild. So the first one is probably the deepest conceptual step, which is the connection between the stochastic six-vertex model and the ascending Hall-Littlewood process, which is a known result from the work of Borodin, Buffetov, and Wheeler. And what this step does for us is that it completely recasts the question from the six-vertex model to the Hall-Littlewood processes. And the benefit of working in this framework is that you have the toolbox of the McDonald difference operators that allow you to compute joint observables for this process and then study those observables asymptotically. So that's the sort of main algebraic component of it. Now the formulas that I'll show you what the formulas are. So they are expressions that for something that is supposed to look like the joint cumulative distribution function. It's not going to be exactly that, but it's going to be some quantization of this function. And the formula is going to look like a Fredholm determinant. Okay, so it's not going to be exactly a Fredholm determinant, but it's going to be given by a series that kind of looks like a Fredholm determinant. So once you have these prelimit formulas, the game is very simple. So you simply look at your formula and you try to show that each summand has a limit as m tends to infinity. Then because you show that the summands converge, you need to show that the full series converges. So you need to exchange the order of the sum and the limit. And for that, you need to have uniform control of the summand. So these IMs need to be uniformly in M bounded as functions of N1 and N2. Once you know you can exchange the order of the limit and the sum and you can compute this limit, then you have some answer, some limiting formula, and you just need to match it with the Fredholm determinant formula for the Airy process. Now you can imagine that this last step is fairly simple. Once you have a formula, it's a computation to show that it matches the answer. So I will focus today kind of at least explain the first step and then focus on steps 3 and 4. So that's the goal for today. So what is the ascending Hall-Littlewood process? So it is a measure on an increasing sequence of partitions. So they're labeled lambda 1, lambda 2 up to lambda n. And graphically, I just represent them in this way. I just write the parts of each partition diagonally down. And the model depends on two integer parameters, capital N and capital M, as well as parameters X and Y that are numbers between 0 and 1. So the measure of a given sequence of partitions is up to a normalization constant given by a product of what are called skew Hall-Littlewood polynomials evaluated at the x's times a Hall-Littlewood polynomial or the dual Hall-Littlewood polynomial evaluated at the y. So if you've never seen what these objects are, that's okay. We will not be using them in this talk. So these are important special functions. They are special cases of what are called the McDonald symmetric functions, and they have many nice properties. So I want to mention that this process is it depends on the parameter t implicitly. That's one of a parameter that's built into the definition of the Hall-Littlewood polynomial. So these polynomials depend on the parameter t between 0 and 1. And the McDonald ones have another parameter q that currently is being set to 0. The other thing I want to mention is that, a more general framework of McDonald processes was introduced and studied in a paper by Borodin-Corwin. So if you're interested in learning more about the special properties of these objects, you should go and read that paper. It's a very good paper. Now we're going to be working with the homogeneous version of this model when all the x and y parameters are set to the same number a. So when you do this, this entire probability distribution depends on just two numbers, little t between 0 and 1 and little a between 0 and 1. So now let me explain how this model relates to the six-vertex model. What we have here is this ascending Hall-Littlewood process. It depends on two parameters, a and t. And what you do is you just follow the bottom boundary of this picture. Or equivalently, you just go one diagonal slice at a time and you count how many boxes do you have. So here there's like an empty diagonal, so there's 0 boxes there. And you have a single box, so you write 1. You have 2 boxes, you write 2. 3 boxes, you write a 3. Another 3 boxes, you write a 3, and so on. And in this way, you obtain a sequence, an increasing sequence of numbers. Now these numbers are nothing but the lengths of these partitions, or equivalently their largest column. That is typically denoted by lambda 1 prime. 1 is for the first column and prime is that it's a column and not a row. And so for any random sequence of increasing partitions, you can form this increasing red curve that I plotted here. Now let me remind you that the six-vertex model depended on two parameters, little b1 and b2. And the height function, which was just counting the number of arrows, was a decreasing blue line that's written down here. And then the statement by Borodin, Buffetov, and Wheeler basically says that if the parameters of the two model, B1 and B2 and A and T, are related through these two equations, then the red curve and the blue curve have the same law, except that you need to reflect the red curve and shift it. Okay. So here you need to reflect, this is this minus sign here, and shift it up by m, and then this curve will have the same distribution as the h. And what this basically tells you is that if you're interested in understanding the asymptotics of h, you might as well just work with lambda 1 prime, because the question is equivalent. Okay, the two curves have the same law. So right, so the benefit, as I said, of switching to the Hall-Littlewood process is that you have the McDonald difference operators that allow you to compute stuff there, like joint observables. And I will, unless I have an abundance of time at the end, I have some slides at the end of my talk that discuss this, but I will skip the steps of the derivation of the formula and just tell you what it is. So brace yourselves, it's this equation here. But let's try to digest what's written here. So on this side of the equation, you have an expectation. So this is with respect to the Hall-Littlewood process. And what you have is a product of two functions. Now this is 1 over the Pohammer symbol that Elisa mentioned in her talk. I recall the formula down here. It's some simple function involved of 2 arguments. And this blue function is sometimes called the t exponential function. So this is a deformation or a quantization of the exponential function. And so you should treat this expectation as a joint Laplace transform, quantized Laplace transform. Okay, so that's what's written here. And in general, people, experts in the area, know that one can obtain the asymptotics of these lambda 1 prime at n1 and n2 by studying the limit of this expression, because asymptotically this actually looks like an indicator function, so you can use it to access the convergence, the joint convergence of these things. So the formula that we obtain is that this expectation can be rewritten as a double sum of certain terms im, n1, and n2. So what do these look like? So these are 1 over n1 factorial and n2 factorial. So people that have worked with determinantal point processes, they know to expect this term at the front. And then you have a quadruple kind of contour integral formula. So there's gamma 1 and gamma 2 that You have n1 copies of them, and then you have gamma 3 and gamma 4 with n2 copies of each one. Now the gammas are just concentric circles that are centered at the origin with radius r1, r2, r3, and r4 that are just decreasing. And you have some conditions on them. So if you multiply the largest circle by t, it needs to be inside of the smallest circle. So that's what this condition here means. The smallest circle needs to include this parameter a that was kind of in this expectation in defining the Hall-Littlewood process, and a inverse needs to be outside of the largest one. So those are basically the only conditions on these contours. Now what's written inside? So what's written inside is a product of three types of terms. There's the blue terms, there's the red terms, and then there is a purple term. So the blue term is a product of a d function, which is just a Cauchy determinant. So the d function is just a Cauchy determinant. The g function is just a rational function of the z and the w variables raised to some high power. And then it's multiplied by something that I call the spiral function. I'll explain in the next slide what the spiral function is. And what I want to mention is that in this formula, if you just keep all the blue terms, so if you just keep this d, g, and this n1 factorial and the gammas, you'll exactly obtain the expectation of this Laplace transform. And if you just keep the red terms, you'll get the expectation of this Laplace transform. What happens when you take the joint Laplace transform is that you obtain a brand new term that is now in purple because it's between D and red and blue. And this new term is CT, stands for cross term. And this cross term is just a double product of product of ratios of Pohammer symbols, okay, that involve the ZW variables and the Z hat and W hat variables. Now, to people who are familiar with some of the physicist work or the work on the low gamma polymer, the cross term is expressed as products of ratios of gamma functions, but because we're working in the discrete case, this is actually related to Q gamma functions rather than gamma. So this is what the formula looks like. The only thing I didn't explain is what is the spiral function S. I'll tell you what it is on the next slide. So this spiral function is basically just a wraparound of the function 1 over sine. So what the first equation that I've written here is what's called the Mellin-Barnes representation that allows you to rewrite an infinite generating series as a vertical contour integral. And essentially this equality is subject to some technical conditions on G that I will not bother with, is essentially just computing this, this integral as a sum of the residues using the formula for the residue of sine at the integers. Now, because this function is not a function of S, but a function of t to the s, if you integrate it over a vertical contour, it becomes periodic. So what you can do is you can just split this vertical contour as a sum over translates of a fundamental domain for this t to the s, and then just pull it outside of the sum and apply a logarithmic change of variables. And that's how you get this function s. It's basically just upon a logarithmic change of variables, this sine function, except that you need to sum over the possible translates, integer translates of your fundamental domain. The benefit is that now the contour is a circle and not an infinite line, which makes the formulas more symmetric. Okay, that's the benefit. Let me explain somehow maybe a convergence problem that maybe I think is important. Well, it is important. Namely, we have in our formula a double sum of these guys over n1 and n2. So currently the capital M is fixed. We're not letting it go to infinity yet. It's just fixed integer. We want to understand why can we sum this expression over n1 and n2. You can bound some of the expressions in this integral formula. So you can bound the g functions by some constant to the n1, and these functions are completely benign because you have factorials here that help you control these terms. There is an immediate problem, however, with the cross term, because pointwise there are points of the arguments where it grows like e to the constant times n1 times n2. So if these two are equal to each other, this cross term is growing in absolute value like e to the n squared, whereas these factorials are giving you decay of order e to the n log n, and that's not enough to control this cross term. Now, the typical thing that people do with the Cauchy determinant is they use Hadamard's inequality to bound. If you apply Hadamard's to the Cauchy determinants, you get this bound, which is also not helping you converge. So currently, there is nothing capable of handling this cross term. And so the key observation is that the Cauchy, applying Hadamard's inequality to the Cauchy determinant is entirely too crude, and one needs to utilize some hidden decay properties of the Cauchy determinant to even get the prelimit formula to converge. So there are a few bounds on the Cauchy determinant in the paper. There's 3 of them. I'll give you the simplest one here, and this is the only statement that I will prove today. But it's a very simple thing. In fact, this is the whole proof that you need. So you fix 2 real numbers, little r and capital R, with capital R being bigger than a little r. And then you have the following estimate of the absolute value of the Cauchy determinant. It's bounded by r to the minus n times n to the n times the ratio of the radii raised to the n choose 2 divided by this denominator. And this is true if the z variables all have size or an absolute value equal to capital R, and all the w's are smaller than or equal to little r. And what I want you to notice is that if the ratio of the 2 radii is small, like let's say 1/10, then this number is going to quadratically exponentially in n decay, right? So it's going to be like e to the minus a constant n squared, because this ratio is going to be less than 1. So how do you prove this thing? Well, it's very simple. So you simply apply the Cauchy determinant formula and divide both numerator and denominator by r to the n squared. That's all that's happening here. And then you just call the numerator a and the denominator r to the n times b. So b is just this double product here. So this r to the n is exactly going to correspond to this r to the minus n. So we just need to upper bound a by this thing and lower bound b by this thing, and then we'll win. Now, to bound the a, all you're using is just the fact that it's a product of 2 van der Monde determinants, and you can apply Hadamard's inequality to each one. So if you apply Hadamard's inequality to this van der Monde, you get this bound. And if you apply Hadamard's to this one, you get this bound. That's it. You bound the A. Now for B, you just notice that Z over R is a complex number of absolute value 1. So it's on the unit circle, whereas this one is on a circle of radius less than little r over capital R. And then you have 2 concentric circles and you want to bound the minimal distance between them. Well, that's just the difference of the radii. So you get this lower bound for B. So immediately you have this this inequality. Now, if you apply this inequality, so here I've drawn the 4 contours. This is gamma 1, gamma 2, gamma 3, and gamma 4. So if you apply the previous lemma, this is the bound that you get on the Cauchy determinants. A simpler, in fact, even a simpler computation than the one I showed in the previous slide allows you to bound the cross term in terms of the ratio of the radii. So if you know that your variables lie on certain circles, you can get this bound more or less for free. And so now what I want you to notice is that if the ratio of the radii is very small, then this is going to look like a 1, or at least a small number bigger than 1 raised to the power, because the Pochhammer symbol at 0 is 1. Okay, maybe people cannot immediately tell, but that's the case. On the other hand, if the ratio of the radii is small enough, then this guy are going to give you quadratic in N1 decay exponential, and the Cauchy determinants are going to be enough to kill the cross term and make this summable over capital N1 and N2. Now the question is, well, can we always deform the contours in this way? So because what you need to do is you need to spread them apart. These contours really need to be spread apart. And there are things preventing you from doing that. A mild thing that can be circumvented is the little a, because your formulas are only valid if little a lies inside of the smallest contour and a inverse outside of it. So that's preventing you from spreading these contours apart. But of course, if a is small, you can do it. The other condition is that you want the smallest contour, which is this innermost circle, multiplied by T inverse, which is this dashed circle here, to be outside of everybody. And so that's another restriction that prevents you from spreading these contours apart. But of course, if T is small, you can do it. And so as long as A and T are sufficiently small, you can use these bounds and get the prelimit formula that is convergent. This is one of the sources of the parameter restriction in the main theory. Let me talk about limits and asymptotics. So the first thing is you want to understand the limit of this expression. So you fix n1 and n2, and you want to let capital M tend to infinity. Your argument is you want to use steepest descent. But the problem is that your contours are not arranged along steepest descent course. So the W variables, they want to be slightly inside of the unit circle, which is the dashed line here. And the Z variables want to be outside. That's where they decay, the functions here. So what you need to do is you need to take this Z hat contour and push it outside, and take this W contour and push it inside. So you want to rearrange the contours in this way. Now, as you're performing the contour deformation, the cross term, you're crossing poles when W is equal to Z hat. They're simple poles that you're crossing. And so you just get a sum of residues, but the sum is finite. And each one of these new functions is equally easy or equally difficult to take the limit of. So it's fine. You just need to compute it. Even though kind of the structure of the formulas is basically the same for any K, I'm just going to stick with K equals 0, because then I can just copy the previous formula and not write something more complicated looking. So what we do here is we just deform the Z hat past the W contour. We get the sum over residues, and we want to show that each of the residues converges and subsequently is bounded by uniformly in M. Now, so all the W contours are now called gamma in, and all the Z contours are called gamma out. And all the gamma ins are just circles inside of the unit one, and the Z ones are circles outside of this. So to get a sense of how the structure of the formula, to get a sense of what is happening inside, there is a nice trick that you can kind of peel off one of the factors in your Pohammer symbol. So you can rewrite your cross term in this way, and all that is happening here is you're just using the functional equation for the T gamma function. You're just kind of peeling off one factor from this infinite product of Pohammer symbols, and you're setting it aside. And the reason you're doing this is because if you take this double product and combine it with the two Cauchy determinants before, you get a master Cauchy determinant, like an N1 plus N2 big Cauchy determinant that is now in the variables capital W and capital Z, that they're just the little W and W hats appended. So this is the vector obtained by appending the two vectors next to each other. And this residual product is what I call CT tilde. Okay. And if you look at the residual kind of expression, the G's, if you remember, these were exactly the functions that you get from the single point asymptotics. And we know how to do the single point asymptotics. We know what the descent contours are. There is a critical point at 1. You can do the usual Taylor series expansion there and get the limit. This Cauchy determinant in that limit will maintain, and in the limit will also be a Cauchy determinant. And the only thing is that this cross term, but if N1 and N2 are fixed, this CT tilde really looks like 1. You can actually show that it converges uniformly to 1, because these Z and Z hat variables, they all go to 1 if you do the deformation. So the termwise limit is the easy part, because you're essentially using the usual steepest descent argument. There's nothing new because the N1 and N2 are fixed here. The question is, how do you bound this term if N1 and N2 are big? So that's the main part of the argument. And before I kind of discuss it, I just want to give you an informal description of how I think about these formulas. Hopefully you will find it useful at some point if you ever work in anything related. But here I've just rewritten the Cauchy determinant as a product of two Vandermonts divided by the double product. And here I've rewritten the G functions as basically e to the m times some functions, S1 and S2. So the superscript is basically reflecting the fact that here I have little n1 and here little n2, but up to first order asymptotics, these functions are actually the same. Now when you look at the formula, the way that I like to think about it is that the Z, W, Z hat, and W hat points are just particles that are living on this gamma in and gamma out. So they're kind of like particle systems on concentric circles. And they kind of have like a logarithmic interaction when you look at the Cauchy determinant, because the you just view that the Z particles are all positively charged, so they repel each other, which is reflected by this van der Waals. All the W particles are negatively charged, so they also repel each other. But opposites attract, so that's why you have this double product in the denominator rather than the numerator, because they are attracting each other. So this is like a logarithmic interaction term, this Cauchy determinant. The G functions act like an external potential. So if these contours are actually descent contours for the S functions, then if M is large, this is going to penalize particle configurations that are have particles away from the critical point. So they are really trying to push all the particles to the minimizer of this exponent. And so they act like an external potential in this way. So this is forcing them to repel. This is forcing them to kind of converge to the critical point. And the cross term is like a special type of interaction between hat particles and non-hat particles, which is completely, I don't have an analog for that. It's just a special type of interaction. Okay, so we're going to come back to this interpretation in a little bit, but for now, let me just tell you kind of how what is the type of bound that we can obtain. So remember, we want to take the limit inside of the sum, so we need to be able to justify the taking the limit and taking the double sum over n1 and n2. And for that, we need to control uniformly in n1 and n2 this quantity. This is the control that we can achieve. Here, capital delta is just the sum of n1 and n2, and hopefully you can, if not immediately, quickly see that this is summable over n1 and n2. So this is like a dominating series that will allow you to apply something like dominated convergence, okay? And the way that we prove this bound is by considering three cases. One is like a microscopic case, when this delta is much smaller than m, less than m to the 1/2. There is like a macroscopic case when delta is kind of big, much bigger than capital M. And there is like a mesoscopic case when delta is somehow between m and m to the 1/2. And in each different case, we're gonna kind of see the different parts of the formula help us be bounded, kind of allow you to obtain such a bound. Now, the first case is the easiest one, when delta is very small, because you just deform the contours to the descent contours and you bound the cross term in the simplest possible way. So here I just written down sort of the simplest Taylor expansion bound that you can get. And the point here is that in the potential term, this G function, you have a decay if you move away from the critical point that is of strength capital M, whereas here you have growth at most at size delta. But if delta is much smaller than m, this decay will beat this growth, and you will be able to bound your integral. So in this case, what happens is that the potential functions g are perfectly strong enough to handle the cross term, ct tilde, and the Cauchy determinant is handled by the factorials using the usual Hadamard inequality. So everything is controlled. The second case, which is the macroscopic case, delta much bigger than capital M. So in this case, the strategy is to basically make gamma in into a small circle and gamma out into a big circle so that they become nice and separated. Now, in the process of this separation, from the lemma that I showed you, you know that the Cauchy determinant starts to decay quadratically because the ratio of the radii is becoming very small. So you obtain this bound for the Cauchy determinant. And then you just estimate again in a crude way the G functions. So the G functions now are no longer your friend. They become your enemy because you deform these contours away from their descent contours. So now the G starts to grow. But they cannot grow too quickly because if you look at this function, okay, so this is like a product of order delta, and then something is raised to the power m. So these grow like e to the m delta. And in fact, you can see that the linear term should be proportional to a, because if a is 0, this just becomes 1. So you can immediately kind of get this type of bound. And the cross term also, because you have a double product, it grows like e to the delta squared. And again, you can see that the linear term is proportional to t, because if I plug in t is 0, I just get a 1. And so you see that the Cauchy determinant lives on a, gives you more decay than these guys can grow, because the delta is bigger than m in this case. And so And if you pick little a and little t sufficiently small, you can make the Cauchy determinant win. So this is the other source of the parameter restriction in the main result. And so in this case, what happens is that the Cauchy determinant helps you control everything in this expression and allows you to get the bounds. So in the first case, the G functions help to kill the cross term. In the second case, the Cauchy determinant helped you kill the cross term. In the mesoscopic case, what we will see is that neither of these two individually is enough to handle this cross term, and they need to work together to bound. So let me try to explain how that happens, and that will be the last thing that I'll say meaningful in this talk. So in the mesoscopic case, I remind you, it's the case when delta is kind of smaller than m, but bigger than m to the 1/2, so it's about order m. And what you do in this case is you spread these contours gamma in and gamma out only a little bit. This little delta, which is capital delta over m to the 1/3. So this thing is bounded from above by 1, but it's allowed to shrink, because if delta is like m to the 2/3 or something, this ratio can shrink with m. And so you just spread them apart. Now what I've done here is I draw the arrows in which these S functions grow. So starting from 1, they grow to the right. And then as you move along the circles, they start to decrease. And to kind of bolster this comparison, you should think of these S functions near 1 is locally like z cubed. And if you look at z cubed and you move to the right by delta and up by y, the absolute value looks like this. So as you move to the right, you increase at the cubic rate. And as you move up, you decrease at the quadratic rate. So that's what's happening here. And you can use your formulas for the G functions. They really locally look like this thing up to a constant to get this upper bound. So again, because you have an m here, it gets copied. You have a product of n2 terms, so that's where this delta is coming from. And then you have the delta cube, because that's how the real part moves in the horizontal direction. In addition, you have the decay is now quadratic, which is proportional to delta. So that's the same as this delta here. You have the m, which is just being copied. And then the q is the sum of all of these square distances, the distance to the critical point 1. So that's all that's happening here. Okay, so this is just telling you simple critical point analysis, how this function looks near 1. And I just copied it here. I just copied that inequality here. The cross term you bound again in the crude way that you did before, and you get e to the minus ct times delta squared bound for it. It's the same bound that I showed before. Now, the way that we do we obtain the bound for I is by considering the case when the quadratic term q is kind of big and when it's kind of small. So let me explain how each story goes, and then I'll stop. So if q is somehow big, it's coming with a negative sign. So this potential term is helping you decay, okay? And in fact, if you kind of plug in the values of delta, you'll see that this term is enough to kill both of these. So in this formula, the G functions in case 1 are going to be enough to kill the cross term, and the Cauchy determinant again will be handled by the factorials using Hadamard's inequality, and you'll get the estimate. So in this situation, what's happening, what does it mean that Q is big? It means that a lot of these Z and W particles are away from the critical point. And so your confining potential is strong because it decays very fast as you move away from the critical point, and it's strong enough to control everything. In the second case, Q is small, which means that many of the particles are near the critical point and your potential is not strong there. And then here is the key observation that makes the argument ultimately work, is that there is extra decay in the Cauchy determinant if Q is small. So let me try to at least, I will not be giving you the exact statement or proof of it, but let me tell you why you should expect something like this. So if Q is very small, remember Q is just the quadratic distance of Z and W to 1, it means that the majority of your particles are close to the critical point 1. But now if a lot of these particles are close to 1, it means that they're close to each other. And then the Vandermonde that appears in the numerator of the Cauchy determinant is going to be small and make this thing become even smaller. The kind of dilemma that I showed you before would be able to prove some bound like this, where you have the coefficient being little delta, which is potentially going to 0. But because of this extra decay, you can ensure that the Cauchy determinant decays fast enough, and then again you can kill everything in this expression. Okay, so maybe this is a little bit too technical. Let me just summarize the talk and the paper. So if I have to summarize the paper in one sentence, it would be that it's somehow a proof of concept that you can use the McDonald difference operators to obtain a multi-point convergence result. I believe that there are various people that have worked out various formulas in, using these operators, and for sure it was known for a while that you can compute joint observables. But I think that an important question that people weren't sure about is whether these formulas are difficult. Well, it was clear that they were difficult to work with, but the question was whether they are impossible to work with, or meaning that the formulas are useless, or if the analysis is not strong enough. And I think that now at least we have confidence to believe that the formulas are useful, and we just need to kind of strengthen the analysis part, and then we'll be able to prove these types of multi-point convergence results. In terms of kind of future directions, I think that there's many directions, of course, but the most immediate ones is to extend the formulas that I currently have to arbitrary number of points and parameters, because, for example, this will give formulas for the non-homogeneous six-vertex model that allows to get formulas for the higher spin vertex model, and from there you can degenerate, take limits, and do all sorts of things, with kind of obvious candidates being the ASEP, KPZ equation, and log gamma form. So I guess I'll stop here. Thank you for your attention.
Thank you very much, Evgeni.
My apologies again for the technical issues.
The theme of your talk, right, that there's decay in the Cauchy determinant, reminds me of the Arrested Development quote that there's always money in the banana stand.
Yeah. So there have been at least 3 walls in doing this argument, and every time a wall was hit, it was always the Cauchy determinant that somehow helped climb them. Okay, there's always money in the banana.
Questions for Evgeni?
I have a question.
Yeah, Jeff.
Does your proof of concept with the multi-point analysis, do you know if that says anything or can say anything about multi-species models?
Oh, I have not thought that
okay.
far at all. So it can say something about ASEP, but whether it can kind of, I really have not even begun thinking in that direction.
Okay.
I hope so.
Yeah. Yeah, I hope so too.
Other comments, questions?
So very specific question, like two slides ago or something, you were talking about in the mesoscopic region how you bound with the Cauchy determinant. Mm-hmm. So you said when Q is small, the top terms, the 2 top Vandermonds in the Cauchy determinant will be small, which I agree with. But isn't the product on the bottom sort of the same order, because they're all the particles are close to the 0.1?
Right. So you should look at the proof. The proof is not as simple as that. You just need, you need to do some computation. But the point is that, these Z and W contours, they're a little bit more separated than the Z's. So kind of, even though formally they look on a different, on the same order, this is slightly faster decaying than the denominator. Okay. So it's not an obvious thing. And I didn't tell you the exact statement, so you should go and read the lemma in the paper. I just wanted to kind of, by pointing to the formula, motivate why you would expect something like this extra decay to occur. It's not a proof; it's just kind of looking at the formula. Why might you even look for something like this? Because it's not easy to work with these things, and getting exact statement requires you to write down the formula and compute something.
Okay, and you're saying somehow the idea is that you have some set of Z contours and some set of W contours, and they're both being close to 1 right now, but they're slightly different contours. So the Z minus W is a little bigger.
So the Z contours are circles of radius slightly bigger than 1. the W contours are circles of radius slightly less than 1 in this setting.
Okay.
And then you get some bound. Well, okay. So I mean, the Q is kind of small, but you know this delta is reflecting the distance between these two circles, meaning one of them is like e to the delta, the other one is like e to the minus delta, and so the Q is like small relative to the separation as well. So it's a technical precise statement. So I don't think we can kind of eyeball it here and get this behavior by just looking at the function. You need to write down an equation.
Yeah. Okay.
I'll be happy to talk with you about it if you want.
Thank you.
Evgeni, what are the issues for the log gamma polymer compared to this one?
Right, so the immediate issue is that you have kind of infinite contours, and the cross term is expressed as a product of gamma functions rather than Q gamma functions. So the immediate sort of difficulty of pushing the arguments that I have is that, you know, all of my estimates on the Cauchy determinant are for circles. So one needs to kind of go and look at the lines and think what is the analog there. So I kind of tried to do something, but it wasn't something I could do like in a few days or something like that. It seems that one needs to think a little bit about it. But that's the immediate problem, that kind of the contours become infinite. So you need to know what's happening near infinity. And also you need to know what the behavior of the Cauchy determinant is on infinite contours rather than circles. But I have some ideas, but nothing concrete. But it's important to handle the product of gamma functions, because that's, you see the same product of gamma functions in the KPZ equation. So it's not a minor technicality. We need to solve this.
Any other comments, questions?
Yeah, maybe I have a question, which is, for log gamma and KPZ, you're formally taking Q to 1 though, right? I mean, whatever limit you're taking from the 6-vertex model, that would correspond to Q being taken to 1. But your arguments are somehow intrinsically rooted in the fact that Q is small. So I'm wondering if that somehow manifests itself as another issue that arises when you look at these log gamma formulas and KPZ formulas, or is that somehow magically resolved in these limits you get?
Well, okay, so to, you know, split the question into two parts. So immediately I cannot take a limit of my formulas to KPZ, because that requires Q, as is the case, T to go to 1 to get to the weak asymmetric limit, right?
Yeah.
And my formulas are only kind of provably convergent if T is small enough.
Yeah.
So that's why I think it's important to first get formulas for arbitrary T and X and Y, so that I can at least figure out how the limit should go. So that's one part of it.
Yeah.
The other part of it is that, you know, I believe that the asymptotic analysis will be different if T, you know, if you take the T goes to 1 limit, because you are dealing somehow with gamma functions rather than Q gamma functions. And it's not clear to me whether, you know, it might turn out that it's easier. I don't know. I haven't, you know, I've spent maybe half a year thinking about this context and maybe a week thinking about the gamma case. For sure it looks different, but I'm not convinced that it's necessarily harder, but for sure it looks different. So one needs to kind of delve into each of the terms in your formulas and try to understand how each of them behaves. And I haven't had a chance to do that yet.
Okay. Thanks.
Okay, well, anyone else have comments or questions for Evgeni? Okay, so if not, I want to thank Evgeni and Elisa for 2 very nice talks this morning. And we'll come back next week, I think, think we have Alan Hammond as the speaker. Let me double check. Yeah, so we have Alan speaking at 1 p.m. Eastern time, which is, I think, 10 a.m. his time. So hopefully he'll be out of pajamas by then. So, okay, anyway, I'll have a very good weekend, everyone, and I hope to see you next week.